We've talked about different patterns before. Specifically, we're going to be looking at geometric sequences and series today. When we're talking about a geometric sequence, this is where your sequence or your pattern is being multiplied by some number each time. So looking at this, I've got 2, 4, 8, 16, 32. So each time you can see here that we are multiplying by 2. Okay, so that multiplication by 2, this would be my R. My A1 term, or G1 I should say, would be the 2 because that's my first term in this sequence. So just to kind of give you a base geometric sequence, you're multiplying by the same rate each time. There's a couple different formulas in terms of that, whether you're talking about an explicit or whether you're talking about a recursive. So the explicit definition, and remember explicit was where like I can give you what is the 100th term and you could substitute that in and you don't need to know all of the other terms prior. And then we have the recursive where it's all based off of the prior term. Okay, so an explicit formula is in the form of an. I should stick with a G because that would make sense, geometric. The geometric is Gn equals G1, which is our first term, times R to the power of n minus 1. Okay, where n represents the term number. Okay, and we've talked about that before. When we were having our common difference was a plus or minus of a certain number. Now we're just multiplying by a certain number. The explicit formula, we have Gn equals. So we always want to list with the recursive formula what is the first term. And that's because n is 1, aka first term. So then after that, it's our previous term, which remember is denoted with that n minus 1 to represent the previous term, times r. So that's our difference between our explicit formula and our recursive formula. One, you're just taking the previous term and multiplying it by a certain number each time. The other one is actually you could substitute in whatever term you need. So with that being said, there will be times when you'll be asked to write an explicit or recursive. We're going to do both just to get both of them out of the way. So looking at this, we're going to be using an explicit and recursive formula. So let's say that I have my sequence is negative 64, negative 16, negative 4, negative 1, dot, dot, dot. Okay? So our explicit, looking at this first term is that negative 64. What's happening each time? So if you're looking for that common ratio, remember it's G2 divided by G1. That's going to get us our ratio. So in our case, we have negative 16 over negative 64, which is going to give us 1/4, which is our R value. So our explicit formula, G sub n is negative 64 1/4 to the power of n minus 1. Our recursive, gn equals, so we would write down negative 64 for n equals 1. And then our previous term, so we would just write down gn sub 1 times 1/4 for anything greater than 1. So just the difference between the explicit and the recursive there. Big thing is, to find the rate, you might want to write that down. The rate is that G2 over G1. That's going to get you your common ratio. You could also figure this out if it was like G3 over G2. The rate should be the same each time. Now, with every sequence, there comes a series. And remember, a series is where you add all of your numbers together. So there's a formula for this in which we can easily solve stuff for. This formula can be written in a couple different ways, whether you're using sigma notation or just regular notation. Sigma notation, remember this is sigma. Sigma just means you're going to add everything together. So you're starting with your first term, you're going to whatever happens to be your last term in that situation. G1 r to the power of m minus 1. Or, this is the formula I like to personally use generally more, is G1 times 1 minus r to the power of r n over 1 minus r. Personally, like I said, I like to use the second one just because I'm not dealing with that sigma notation. So it's a little bit easier. You just kind of, plug and chug right into that formula. So let's look at how to use this information. So let's say that we have a formula here, or a pattern that gives us -7, -42, -252, ... And then they give us an ending here of -5, 4, 4, 3, 2. Okay, so there's a couple different things here that we know and what we don't know. So if I'm trying to use that formula on the right, I have G1, no problem, that's -7. I can find the R, because it's -42 over -7, which gives me 6. But I don't know that N. And that it kind of creates a little bit of an issue, but not really, because we can solve for that and figure it out in order to use our series. So we're going to use our formula here of our geometric sequence. We have G of n. G of n is our last term. So we can plug this information in order to solve for n. N happens to be in the exponent, which means we're going to actually have to use logarithms in order to solve this. So we have -54,432 equals -7 times 6 to the power of n minus 1. Okay, so now we're going to go through and actually solve this. Algebraically, divide by that -7. When we do that, we get 7,776 equals 6 to the power of n minus 1. Using logarithms, I'm going to make this a little bit easier. So I've got log 7,766 equals n minus 1 log of 6. Okay, not a big deal. Divide by that log 6. Too many sevens. And then, of course, we'll add 1 over. Sorry, just working on my calculations here. So I now have that n value. I have enough information now to find my series, aka my sum. Okay. So Remember, this is our general formula here. So in this case, G1 was -7. We got 1 minus 6 to the power of 6 divided by 1 minus 6. So looking at this, I just plug in my information and calculate it. Up on top, I get a very large number, but divided by -5. And my sum slash series is going to be -65,317. So a little bit of review using those logarithms in order to solve, but very doable in order to find that sum.